And in this class, we will also revisit some of the concepts from the matrix algebra so that we can understand this spectral clustering better. So let me know if my screen is visible. So is my screen visible?
Yes, ma'am.
Okay. Okay, so I am just giving the recap on spectral clustering from a different set of slides. I will upload this, and this is very similar to actually what we have discussed. It just contains the explanations also in graph. Okay, so as we know, as we know that data clustering, we have seen in the example that why we go for spectral clustering versus k-means, because the clusters themselves look very different when we project them on a two-dimensional space. So we will go to k-means clustering after this. Actually, we should have done the other way round, but I I kind of messed up the ordering. So in K means, as we will see that what we try to see is the compactness of the data points. So basically, as you can see on a plane, the more compact the data points are, we group them. Like in K means, like in the mixture model, like the Gaussian mixture model. You may don't know about Gaussian mixture model, but you may have heard about the term. So what they basically do is that based on the closeness. But when we are in a graph plane, maybe connectivity matters more than the apparent compactness. So these clustering approaches like spectral clustering, they look into the connectivity part. So if you recall this photo that we have seen, okay, can everyone please keep your microphones on mute? So this kind of image segmentation, we don't need clustering in sense of like compactness, but we need connectivity to identify this is the face, this is the hair, this kind of thing. Now let us go back to this. So we discussed why uh, what is a graph data? That is a set of nodes, what we call vertices, and a set of edges. The edges may or may not have weights. So when we try to do graph clustering, what is our goal? That given data points x1 and xn and similarity w between xi and xj. That means first we need to construct the graph based on this is data point and this is similarity, this is my graph. And we need to partition the graph in such a way that the similar points are in the same group and the different points are in a different group. So partition the graph so that edges within a group have large weight and edge across the group have smaller weight. That is, inside the cluster we have large connectivity, outside the cluster we have lesser connectivity. So how do we do that? But we have read the mean cut algorithm, that we will come up with the two clusters between which the weight of the edges will be uh, minimal, right? So, and we have seen that when we construct the similarity graphs, we have used something called a Gaussian kernel similarity function. So basically, when we have a set of data points and when we have similarities, we need to define the similarities in some way, right? So if you think in ideal setting, it may be the case that all the nodes or all the data points are somewhat similar to all other data points. So will we go for a fully connected graph then, or we will have a threshold for similarity? So for that, we need to model local neighborhood relations between data points, because if it is a completely connected graph, then like partition, then how do uh, that may not be appropriate for many of the applications. So one example that we saw is called the Gaussian kernel similarity function. Again, we will not go into in depth of this, but Gaussian, I think you recall the normal probability the distribution, the inverted Braille graph, that is a Gaussian distribution. Okay, one of the Gaussian distributions. So uh, this so how do we define the weights? For most of the applications we will take like the weights will be given, like the degree, the weights between two connected edges will be given, and we will work on the weight matrix and the adjacency matrix. But a simple idea how the weights are even assigned at the first place is based on a Gaussian kernel similarity, which is nothing other than between two nodes I and J, the weight is defined uh, like this, the L2 norms of the two edges by this 2 sigma square, which is the variance. So basically this control the size of the neighborhood. Okay, so to basically define that, like how we like come up with the edges between pair of vertices, and whether all pair of vertices will have edges between them or not. So from this cluster data set, we can come up with this graph. Okay. So now let us go into graph partitioning. That so we have seen that we partition the graphs generally according to the mean cut. Okay. So what mean cut is that partition graph into two sets A and B such that the weight of the edges connecting vertices in A to vertices in B is minimum. So or that means that inside the group A, my sum of the weight of the edges will be greater than the across the group. So I need to minimize these weights, right? These edge weights. So that is my mean cut. So how it is defined? Cut A to B is the sum of the weight of the all the edges from A to B. Okay, fine. So now this is an easy to solve algorithm of in the order of V cross E. That means number of vertices cross number of edges. Okay. Basically, I need to see all the combination of edge summation of edges to understand which set will be my minimum. But it is not a very satisfactory partition, because what happens in this case by the very definition of the algorithm, it tried to identify the isolated vertices or very lessly connected vertices, because they have like across the across the group weights will be much lesser. For isolated vertices, there will be no edges to other vertices, right? So they will be isolated. So by mean cut, we will come up with some cut like this. But our ideal cut may not only be the mean cut. In this case, say if the data points look like this, our ideal cut may be this. So for that, we go to the normalized cut. Now let us again go to the recap of what is the degree cut and normalized cut. I know this is a bit we are hustling between them, but as I don't have the blackboards right now. So just a quick recall, the degree of nodes are the sum of all the weights originating from a node. Right now we are not separating in degrees and out degrees in a directed graph. Okay? So volume of a set is equivalent to sum of all the degrees of the node. So last day we did the exercise and we see basically for the volume of a node what happens, that all these in between edges they get counted twice and the across they are counted once. Cut AB as we have seen is the sum of the edges across the two partitions, two proposed partitions, which is in this case is 0.3. And our goal is to find the partition that minimizes the cut. But why we are normalizing? Because as we have seen, not every time the mean cut gives us the ideal cut. So how do we normalize? So normalized cut of A comma B is equals to cut of A, cut AB, cut of AB, which are both are normalized by their respective volumes of A and volumes of B. Okay. So basically it becomes like cut of AB into this quantity, volume of A plus volume of B by volume of A into B. And these are minimized when we have these two are equal, volume of A and volume of B are equal. So because as you can see that this quantity to be minimum, uh, if only these two are similar, then this one, like if it becomes square of one of the quantity, then this whole thing is minimized. And this encourages a balanced curve. So we will see what this means in terms of like when we say volume of A and volume of B. If it's similar, then it is minimized. This quantity is minimized, or otherwise one will be greater than other. So it will be always. So any question till this point? Okay. Okay. So let us move ahead. So now, why we are normalizing this using the volume? Because what we are trying to say that we want to partition the graph into two sets A and B such that the weights of edges connecting vertices A and connecting B is minimum, which is similar to this, and we are adding a condition that size of A and size of B are very similar. The reason being that if we add the conditions of size, then the isolated vertices will not be just identified as part of this mean cut algorithm. As you can see that if you need to take into account the size also, then it is very likely that we will have the ideal cut solution, or we will have a better cut or more appropriate cut for our application, because overall we are going to apply it to some real life problem. So that is what is at least our objective in this case. Okay. So that actually we come up with a cut like this where the two clusters are very same in size, and also their partition has the minimum weight. But the problem is that this balanced normalized cut is an NP hard problem to solve. So for that we do spectral clustering. As you know that we just cannot come up with the algorithms to solve NP hard problems. So how we go about this spectral clustering? So now we will go into a bit of matrix algebra. So how many of you remember or know graph Laplacian and the eigenvectors and eigenvalues? Can I have a quick set of hands? That if you recall that, don't.
Can you just tell us again?
Yes, yes, Aditya, can you please repeat?
Can you please briefly just tell us what it is again?
Yeah, sure. Actually, that was my objective, but I just wanted to understand better. Okay, so a graph Laplacian is a graph transformation that we apply an operation on the adjacency and the degree matrix of the graph to come up with a new matrix, which is called the Laplacian transformation. So basically, as I have also said in last week, that whenever we are representing a graph in a computer, it is basically by a form of matrix. It can be either adjacency matrix, can be either degree, or can be degree matrix. So let us take a simple graph. Okay, I have one request. For this part, can you all please take out a pen and paper and please write it down? It's not that you will not get these resources, but if you just write them down, I feel that you will learn better and you will understand better, because ideally we do this in the blackboards or in the whiteboard, but as we are in an online mode, we are showing from slides. But please write it down just for practice. You can memorize later from the resources, PDFs, internet, wherever you like and is convenient. Okay. And if you need more time to write down, please let me know to pause. I will pause. But at least these kind of equations and equalities, please write them down. It will be helpful for you to understand, because that is just a practice, and your muscle will also learn that how did we do Laplacian. Okay. And please feel free to ask me any questions wherever you need. So let us have a simple graph G with n vertices V1 and Vn. This is from simple Wikipedia. Okay, nothing complex. And so the Laplacian on the graph is defined element wise as, say, in the Laplacian matrix, the element Lij, that is in the ith row, intersection of the ith row and jth column, will be degree of the vertex Vi. If I equals to j, that is the diagonals, will be minus 1 if I not equals to j and Vi is adjacent to Vj. That means if there is an entry in the graph adjacency matrix, and it will be 0 otherwise. Okay. So this matrix we can derive by subtracting the adjacency matrix of the graph from the degree matrix of the graph. So in this case, we are not looking into the weights. Say this is a simple graph. So like this 1, 2, 3, 4, 5, 6. So this is the adjacency matrix of the graph. As you see, all the entries are either 1 or 0. And this is the degree matrix of the graph. So let's see. For 1, we have the degree 2. For 2, we have the degree 3. And you may also notice that the degree matrix is a diagonal matrix. Because of course, like, there cannot be degree of one vertices between 1 and 2. It will be a vertex 1, vertex 2, like that. And contrary to that, as generally we assume the graphs do not have the self loops, the adjacency matrix has all the diagonal elements as 0. Okay. So then what happens? If we subtract the degree, the adjacency matrix from the degree matrix, we get the Laplacian matrix. And you see it matches. So this entry, the first diagonal, is, what did we say? That if it is I equal to j, the Laplacian entry will be degree of the vertex I. So that means the degree of the vertex 1, it is 2. And if say 1 and 2 are connected, so the entry will be minus 1. So this is minus 1. Okay. And 1 and 3 are not connected, so the entry will be 0. So this is 0. So it is it's clear, the basic definition of Laplacian. Yes.
So in case of
Yes, ma'am.
weighted graphs, it will be the Lij equals to the weight of the age between I and j if Vi is adjacent to Vj.
Yes, because then the degree is defined as the weights, right? As the sum of the weights.
Okay, so it will be no. I am talking about the adjacency matrix.
No, adjacency matrix is the connectivity.
So
Adjacency.
it will always remain 1 and zeros, even in case of weighted graphs, or in the adjacency matrix there is a weight in
No,
each of
yes,
the.
yes. For weighted graph, it will be weights.
So for weighted graphs, -1 will not be there, right? In the previous definition.
No, weighted graph minus 1 will be there. Okay, let me come to the weighted graph. Okay.
Okay.
Yes, so as you can see, the row and column sums of the Laplacian matrices are all zeros. That is, if you take the row wise sum and the column wise sum, it will be all zero. So now why do we do this Laplacian transformation? Because there are some theorems like Kirchhoff's theorem. If any of you have done graph theory, so the thing is that on Laplacian we can actually derive the graph mean cuts, and we can do these spectral clusterings. Okay, as we will see, these spectral clusters are basically defined by the second eigenvalue of the Laplacian matrix. So this Laplacian of a graph is helpful for other kind of operations on the graph downstream. Okay, there is another thing. For a directed graph, the adjacency matrix is not symmetric. So directed graph means, like, say I only have edge from 1 to 2, but not from 2 to 1, as we have discussed. But now the thing is that for these operations like spectral clustering, these operations are technically defined on a symmetric graph. Okay, for the symmetric matrix. So for that, what we do, we symmetricize the adjacency matrix. I do not need to go into the mathematical details. It is done by summing up in Boolean method the adjacency matrix A and A transpose. Okay, so Boolean sum is basically OR function, right? So the 1 plus 0 becomes 1. 1 plus 0 becomes 1. So this is just a Boolean sum. So the matrix is symmetricized, and then on top of that we apply the this Laplacian transformation. So this is just for your knowledge, that even if we have an asymmetric graph or a directed graph, but we generally transform on the symmetricized version of the adjacency matrix. Okay. Is it clear till now?
Yes, ma'am.
Can you repeat how we symmetricize it?
Basically, what we do is that we sum up adjacency matrix A and A transpose. So what is a matrix transpose? Basically, you are transposing the matrix across the diagonal, right?
Yes, ma'am.
So as you can see, like, this entry is 0. So basically, what does it mean? That there is a node from 1 to 2, but there is not a node from 2 to 1, right?
Yes,
This is 0 and this is 1, right? So similarly, there is a node from 1 to 3, but there is not a node from 3 to 1. So that is how it is defined, right, for a directed graph. So basically, for all the 0, like these asymmetric entries, we take the Boolean sum. So what? So you remember the Boolean and Boolean OR, right?
yes, ma'am.
Yes. So what happens? If it is 1 plus 0, then the result is 1. If it is 0 plus 0, then the result is 0. So basically, we are not doing a summation. We are just transforming the adjacency matrix by adding up its adjacency to transpose matrix. So basically, to get a symmetric matrix. Okay.
Ma'am, this symmetricized adjacency matrix is the adjacency is actually the adjacency matrix of the
Can you
corresponding
can you?
undirected graph.
Huh? Yes, yes.
I'm saying that this is the symmetricized adjacency matrix same as the adjacency matrix of the corresponding undirected graph.
Yes, yes, you can assume that if there is an undirected version of the graph, it will be the symmetricized matrix will be the adjacency matrix of the graph.
Okay.
Okay. Yes. 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 Okay. So now the Laplacian is done. Another thing is that we need to know is the uh, eigenvalue and eigenvector from the matrix. So let us go into that. Okay. Okay. So do you uh, so do you recall eigenvectors and eigenvalue? Okay, so let me go and again a small request. Please write down these mathematical things as we go on discussing, and please feel free to stop me if you need time to write. So basically, for a for a matrix, eigen vector v is defined as a like scalar vector as an as a vector v, and there is an eigenvalue which is defined as lambda. So basically, the eigenvector and the eigenvalue of a matrix need to satisfy the this equation that m into v, this is matrix multiplication, and so v is a column vector, is equals to lambda into v. Okay, so now let us consider a symmetric matrix n cross n. Then let us see what will be the dimensionality of this matrix operation. This will be n cross n, and this will be n cross 1, right? So the resultant matrix will be n cross 1 from simple matrix multiplication. If we have a matrix of dimension n cross n multiplied with a matrix of dimension n cross 1, so that the resultant dimension will be n cross 1, and this is a scalar quantity. So a scalar quantity multiplied with n cross 1, the resultant dimension will also be n cross 1, right? So we see that the dimensions, they are equal on both the side, and that is how an eigenvector and eigenvalue of a matrix is defined. How to find eigenvector and eigenvalue is yet another thing, but this is the definition of what is called as an eigenvector and an eigenvalue of a matrix. So generally there are more than one eigenvector and eigenvalue of a matrix. So as I said that we will deal with the symmetric matrices like n cross n matrices. Okay, and you can see for a graph, if there are n nodes, so all the matrices will be n cross n, right? And it will so why we deal with the symmetric matrix, and why we do spectral clustering on transforming a matrix to a symmetric matrix, because there are some special properties of the spectra of the matrix. So these spectra are basically like spectra refers to the matrix eigenvectors and eigenvalues. That's why this is called the spectral clustering. Okay, that's how the name has come. So what happens that say if v1 is the first eigenvector or the one of the eigenvector of M of eigenvalue lambda 1, because two eigenvectors, say if there is a v2 of an eigenvector of M and has a lambda value, sorry, eigenvalue lambda 2, then this lambda 1 and lambda 2 actually are different. Then what happens that if M is a symmetric matrix, these V1 and V2 are orthogonal to each other. That's why we also work on these symmetric matrices, because their eigenvectors are orthogonal to each other. What does orthogonal means? That V1 into V2 will be 0. It is V1 to transpose, because unless you transpose, you won't be able to multiply them because of their dimensions. So basically, if V1 is also n cross 1 and V2 is also n cross 1, right? So then V1 transpose will be 1 cross n. So 1 cross n into n cross 1 will be a scalar quantity. And if V1 or V2 are two orthogonal vectors, as we know, for orthogonal vectors or those vectors which are at 90 degrees with each other, their multiplication is 0, right? And in this case, generally we assume these two eigenvalues of two different eigenvectors are not equal. But if they are equal, then V1 plus V2 also become 0. So you don't need to remember this, just this part. That for a symmetric matrix, all the eigenvectors are orthogonal to each other. Okay. So clear till this part? Yes, no?
Yes, ma'am.
Yes, ma'am.
Okay. So now for every n cross n symmetric matrix has n eigenvalues, and generally we write it in terms of the ascending manner, that if the eigenvectors v1 to vn for an n cross n symmetric matrix and all are orthogonal to each other, okay, and they have all eigenvalues like this, the lambda 1 less than equals to lambda 2 less than equals to lambda 3 less than equals to lambda n, okay, and so on. So for all I, m into vi is equals to lambda I vi, okay, fine. So now in the matrix notation we write it like this, that v capital V is the matrix whose ith column is vi, that is for V, all the difference columns are the VI. So V will have how many columns? N columns. And lambda is this capital lambda is the diagonal matrix whose ith diagonals is lambda I. So basically across lambda, the capital lambda, I have all the eigenvalues. So my so in the matrix notation, then M cross V equals to V cos lambda, because M cross V is equals to this MVI summation of this, and V cross lambda is equals to summation of this. Okay. So why do we do that? Because in this second step, we multiply each side with V transpose. Now what happens? As we are doing eigenvectors on a symmetric matrix and all the eigenvalues are orthogonal to each other. So here comes the need why we define why the property of orthogonality is important. So MV transpose is equals to M, right? Because V transpose will be an identity matrix, and V uh, and this side will be V cross lambda cross V transpose, which actually is summation of lambda I Vi into Vi transpose. And this is important because maybe not right now. This is called the eigen decomposition of matrix M. So this is used in many of the information retrieval operations, like if you have come across the term singular value decompositions, to again kind of identifying pattern and clusters and similarity among data points. Okay. So clear till now? So yes, now let us come to the Laplacian of weighted undirected graph. Now let us look into the weighted graph. So shall I go on? All clear?
Ma'am, M is a
Yes.
matrix.
Yes, yes. Yes,
Is
sir.
M a matrix?
Which matrix?
Can you scroll up?
Yes,
Here, M is a matrix, right?
yes.
So Vi into Vi transpose also will be a matrix. That's why it's a summation of all the matrices of Vi transpose type.
Yes, yes. So VI into VI. So wait, no, VI into VI transpose won't be a matrix, it will be a value. If you do the two, like one will be a column vector and another will be a row vector. If you multiply them, it will be a value. So it will be a value, not some into of matrix.
But the left hand side is a matrix.
Yes, but ideally it should be a value. So because
Ma'am,
yes,
Vi suppose Vi is a value. Vi into Vi transpose is a matrix.
yes. No, vi lambda is the value. Vi is vi is the eigen vector of m, and vi transpose is the transpose of the eigenvector of m.
So now basically the
But summation of but technically this should be a value because is n cross 1. Vi transpose, yes. This will be a matrix. This is an n cross n matrix. Yes, thank you.
Ma'am,
I was
yes, ma'am.
calculation
From here,
other way around. Yes, yes,
from here, what is the use of decomposing M into this kind?
yes. So basically, this eigenvalue decomposition are used in other downstream operations like if you look into the information retrieval to identify connections among data points, say for example among text data, so there's something we called latent semantic analysis. Okay, there is a method called latent semantic analysis to identify the similarity or the connections of different concepts across text data. So that operation stands on something called a singular value decomposition. So this singular value decomposition is again based on the eigen decomposition of the text adjacency matrix. Okay, so basically this eigen decomposition that is used in say is needed in say information retrieval, in other machine learning tasks, in natural language processing. So it may not have any application right now like what we are discussing, but it is useful. So as this comes with the flow, so I thought it will be better to discuss it. Am I
Couldn't
clear?
understand the last line.
Am I clear?
Hello, ma'am.
Okay. Okay. So let us see now.
Think
We have. Yes. If anyone has anything to say, can you please type? Your voice is breaking. I am not able to understand. Please type. So we have seen the Laplacian of a simple graph, the concepts of eigenvector and eigenvalue. So let us see the Laplacians on, as someone was asking, on a weighted undirected graph like we are dealing at this point. So then our graph is defined as a set of vertices, set of edges, and a set of weights W. So the adjacency matrix, as someone has rightly pointed out, now instead of just 1 0, it is the weights between the vertices I and j if there is an edge exists between I and j. Okay. And then the degree matrix of a weighted graph, as we have seen the graph degree is defined in the slides, it will be the summation of uh, all the adjacency values for the particular vertex I. So again, this adjacency matrix has zeros along the diagonals, and the degree matrix has only having non-zero entities along the diagonal. And then this Laplacian is again the same thing, degree of the graph minus the adjacency of the graph. Okay. So now you, someone was asking about the -1 for the weighted graphs. Yes, for weighted graphs, the entries will not only be -1, but still the condition is the row wise sum and the column wise sum in a Laplacian will be 0. Okay. So basically for Laplacian of a weighted graph, what happens that if we are not having an weighted graph, so that if the Laplacian for that is LG, then for the weighted graph, it will be just the summation of the weight between Itehu and V for the each Laplacian entries. Okay. Okay, but let us not think like let us not go into the operation. So the main thing is that for Laplacian, for the weighted graph, we will do in the same way that we did in the unweighted graph. But the only thing is that now we are factoring in all the weights for the adjacency matrix as well as the degree matrix. Okay. See, actually, I forgot till which point I was supposed to tell. Yes. So another thing, why do we do Laplacian? So basically, for an eigenvector v and an eigenvalue lambda of the Laplacian matrix. So the Laplacian matrix is again an n cross n matrix, right? So what we so this condition that V transpose Laplacian V is equals to lambda V transpose V, it is greater than equals to 0. So this condition is important that every eigenvalue of a Laplacian matrix is non-negative. So these kind of matrices are called the positive semi-definite matrix. So Laplacian is a symmetric matrix, and for all the eigenvalues of a Laplacian matrix of a graph is non-negative. That is why Laplacian is called the positive semi-definite matrix. Now the thing is that all the things like the singular value decomposition and the spectral clustering that we do, for that this positive semi-definite condition is very important. That is why we are working with the Laplacian of a graph. Clear till now? Okay. It's just repeating this. This V transpose will be an identity matrix because all the like only the non-zero entries will be in the diagonals, and those will be 1, and as the property of orthogonality is there, all the other vi transpose vj will be 0. Okay, so that is why mv v transpose will be equals to m, and va v transpose, this will be this we can write like this, that summation of all the lambda i's into vi into vi transpose. Now vi has dimension the n cross 1. So vi transpose will be having dimension 1 cross n. So this will be in a will result in a matrix n cross n. So that is how this m is equivalent to this, and this equivalence, this m equals to this. Like, so what we are doing, we are basically decomposing m into summation of matrices, right? So this is called the eigen decomposition of m. Okay. And why will this be only vi into vi transpose? For the same thing, all the other products will be 0 because of the orthogonality. So this you can see, it will be like say I times like summation of n cross n matrices. Now as this is just summation, so the dimension will remain only n cross n, and that will be equivalent to m. Basically we are breaking down m into a kind of, as you can think, into a kind of linear equation. So all the lambda i's are the coefficient of an n cross n matrix plus. So it will be like say alpha into n cross n matrix plus beta into n cross n matrix. Something like that. Okay. Now find Nilanjan.
Yes, ma'am.
Okay. Okay. So let us move into this. So now let us move into the normalized cart and graph problem. So normalized cart is, as we have seen, defined as the cart of a comma b, and by 1 by volume of a plus 1 by volume of b. So in this case, actually what he has not done is basically breaking like doing the summation. So this is same as this. So sorry for the slide. So now let us take if our, a column vector such that each fi is equals to 1 by volume of A if I belongs to A, and minus 1 by volume of B if I belongs to B. This is also defined as 1 and minus 1 in some of the slides from different places. Okay, so basically the idea is that the element of fi will be positive 1 by volume of A if the element is from A, and if it is from the cluster B, it will be minus 1 by volume of B. So then this F transpose Laplacian of the graph into F is like this. It will be summation of Wij into Fi minus Fj square, which will be equals to this based on whether like I or J belonging to cluster A and cluster B. Because if you see, if I belongs to A, it will be 1 by volume of A. If J belongs to B, it will be minus 1 by volume of B. So Fi minus Fj will be 1 by volume of A plus 1 by volume of B whole square. Fine till now. This is the last slide. Tell me, fine till now, like last slide of this class.
Yes, ma'am.
Okay. So this is basically like by rule. So if you derive it from this condition for any of the graph, this will hold. I am not going into this derivation. 1 second. Okay. And then if we take F transpose degree matrix F. So this will be equivalent to di into fi square. Okay. So now for fi, how it is defined? Equal to 1 by volume of A if I equals to A. This is the 1 by volume of A square if I equals to A. Now as this is a square, again if J belongs to B, this will again be positive. Now this will be summation of di by volume of A square and di by volume of B square. Now summation of all the di's for I belongs to A is actually volume of A. Okay, got it. The volume of a group A is equal to sum of degrees of all the vertices in A. So this will again be like the upper and the lower will be cut, and like the from the eliminating the numerator and the denominator, this will be 1 by volume of A, and this will similarly in a manner will be 1 by volume of B. So then my normalized scar become something like this. F transpose LF and F transpose by F transpose DF. So now you can see that we are not taking into account anymore the volumes and all, or the cart A, B and all. We are now purely working on the matrices, on the Laplacian matrix, the degree matrix, and we need to find this F, which is defined, and sorry, and we also defined F, which is defined like this. So is it clear till this point?
Ma'am, what is the definition of cut of AB?
This we have discussed 3 times. Cut of AB is the sum of all the weights of all the edges from A to B. Is it clear?
Yes, ma'am. Yes, ma'am.
Okay. Okay. So thank you. We will end today's class here, and